So we are looking at kinetics and equilibrium, page 214 in the notes. So kinetics, this is a term that we have looked at. It is Greek for the idea of motion. So the kinetics of a reaction tries to identify the amount of time the reactants need to form the products. So here's an idea. As you increase the rate of the reaction, you end up with a faster reaction, therefore it takes less time. Now, in order for a reaction to happen, it's all based on the kinetics or the movements of the reactant particles. So in order for a reaction to happen, the reactants must collide with each other to react. And not all collisions mean reactions, but specifically effective collisions are what we're looking at. And I like to equate effective collisions to like a knockout punch. Okay, so effective collisions are like a knockout punch. So during a boxing match, it's a knockout if the competitor hits his opponent in a certain location, somewhere in the face, but he also needs to hit him with the right amount of force. So for it to be an effective collision, okay, we'll say the angle of the collision definitely matters, like where a boxer hits his opponent on the body, and the amount of energy in during the collision. So I'm going to write amount of energy. So taking that back to the boxing idea, that would be like location and the force of the knockout punch, or the punch that leads to the knockout. And if it's an effective collision, okay, this is what is allowed to happen to the reactants. The reactants are able to break some or all bonds. Now they are free, so now they're able to find or swap partners, find a new partner, and when they find a partner they like better, then they're able to form new bonds. And we've covered that idea before. Now, the order of how bonds break, finding a partner, forming a new bond, this is known as the reaction mechanism. So this is the steps the reactants go through in order to form the products. The details of reactions, they're pretty theoretical. Scientists have been collecting data, but one thing that they do know is that the steps that a reactant goes through to form the products, it is definitely unique to the reaction. Now, the slowest step in that process of reactants trying to form the products is known as the rate determining step. The reaction cannot happen any faster than how fast this step occurs. Okay, now things that impact how quickly a reaction can occur. Okay, so number one, it's the nature of the reactants. There is nothing that you and I can do to change the nature of a particular reactant. So we're going to focus on two major types of reactants: ionics, which outside of chemistry class we refer to as a salt, and molecular structures. So ionic, we typically use a quick look at the elements in the formula, and if it's a metal bonded to a non-metal, we say it's ionic. If it's molecular, then we're looking for all of the elements present to be non-metals. Let's draw a couple of examples so we remember our drawings and how that might lead us into how this fits into the kinetics. So ionics, a salt. Our best example of this would be NaCl. If it's ionic, that means it's composed of ions. And whenever we draw an ionic structure, we always use those brackets. Okay? So we have to put ions in each of these brackets. So we typically start with the cation, which normally is the first element in the formula. So we're going to put the symbol Na. But we've got to think through the process. It's an ion. So Na has a configuration of 2-8-1. But when it becomes a cation, so it's becoming its cation, it loses that electron. So the cation is 2-8, and now there are 0 electrons in that original valence shell. So we have to show it's an ion, we have to show that it's a charge, and it gets no dots because there's no electrons in the original valence shell. The other partner, Cl, must function as the anion. Okay, so if we look at chlorine as an atom, we see 2-8-7, and then it forms that anion, and it also wants a configuration like a noble gas, so instead of losing, it easily gains one, so it says 2-8-8 as the anion. So now it has an extra electron, which means now it carries a -1 charge. It still has its 7 original valence electrons, so we need to put those dots in, right? But now it has one extra, the 8th one, that it got from the sodium. So during the formation of an ionic structure, we see that valence electrons are transferred. Okay, then we look at the molecular structure. Let's do our simplest organic, which is methane CH4. It's all nonmetals, and valence electrons are shared. So when we draw this structure, we have to use our circles of sharing to really illustrate it. So carbon is first, so we put it in the center, and then we create that tetrahedral shape by placing the hydrogens as equally distant around the carbon. And in each bond, we need to put 2 electrons because there's 2 electrons per bond in a molecule. The circles of sharing, so now hydrogen has 2 electrons, so it looks like helium, it's happy. But the carbon, through the sharing process, it now has 8 valence electrons through the sharing process. So the bond here is where they overlap. That's the sharing, versus over here, it's where those brackets meet. That's the association. So, and here is our association bond versus our sharing bond. So ionic structures are associations of ions, so we say it's an ionic bond. Because moleculars result in the sharing, we don't say molecular bond, we say covalent bond, because sharing represents the idea of a prefix of co. Now, in ionic, there is, as we use the brackets to show that the valence orbitals of the ions don't overlap, they remain somewhat separated. But in the covalent over here, we use those circles of sharing, meaning that there is that overlap because of the shared electrons. So shared electrons merging overlapping orbitals are harder to pull apart versus an association where they sit next to each other. Also take a look at the number of bonds. I mean, here in NaCl, this one set of brackets represents 1 bond. So as a general rule, ionics tend to have fewer bonds, and moleculars, each overlap represents a bond, so there's 4 bonds shown here. And as a general rule, moleculars tend to have more bonds present per molecule. So take a look. Ionic solutions tend to react really fast, whereas overlapped molecules tend to participate in slower reactions. So up in these stars, a couple of highlight things. So we want ionics react fast. I guess I'm just going to put it in this lower star. So ionics tend to be faster, than molecules when it comes to reactions as a general rule.